Good afternoon, everyone. My name is Jiawei Xiao. I'm from Shanghai Jiao Tong University Computational Marine Hydrodynamics Lab. And today my topic is two-way coupled CFD FEA method for dam break simulation of an elastic beam. And my speech will contain 4 parts. Let's get started with the research background. It's hard for ships voyaging in rough sea to avoid green water events. And green water events could be divided into 5 classical phenomena with the different vertical velocity and wave vertical velocity. When wave vertical velocity is larger than vertical velocity, it could be called a dam break phenomenon. And this is a classical green water phenomenon. And nowadays, there are many approaches to study the elastic dam break problem, like MPS FEM and SPH FEM. But however, the non-mesh method may cost more calculation resources than CFD. So this study proposed this method to study the effects of dam break flow impacting on the elastic beam. And we come to the numerical method. And in the fluid part, we solved the Raynaud average NS equation with K-omega SST turbulence model. And in the free surface, we used the sorry about it. Oh, yeah, it's okay. We used the VOF method with artificial compression to capture the free surface. And in the solid part, we introduced the generalized alpha method to solve the dynamic problem. And in the coupled part, we used the ratio basic function method to do the data mapping work and introduced the implicit parallel to do the coupling scheme, which allow us to do several iterations within one time step until it achieved convergence. And in Raynaud's average NS equation, the tau Ig replaces the Raynaud stress, which requires additional properties to close the equation. So that led to the creation of many turbulence model. We use the K-omega SST model, which is a common choice. And in the sorry about because I do the PPT in the Microsoft, but this is I'm sorry for the before the check. And in the dynamic problem, the MKC equation is adopted, and M stands for the mass matrix of the structure. K is the stiffness matrix of the structure, and C is the damping matrix of the structure. And we introduced the generalized alpha method to solve the dynamic problem. And the alpha, beta, gamma controls the calculation stability and accuracy. And our program was based on interform solver in OpenFOAM ESI V2306, precise 2.5.0, and calculus 2.20. And it could be divided into 5 parts. And firstly, the fluid part will calculate the surface forces on the structures. Then it's transformed to the OpenFOAM adapter. Then the OpenFOAM adapter mapped the data to the calculus adapter in precise using the ratio basic function mapping method. Then the solid part will calculate the structural deformation and then transform back to the OpenFOAM. And the OpenFOAM will update the mesh by solving the Laplace's deformation equation. The reason why we used precise is that firstly, no need to modify the underlying code of the solver. The precise just run as a library function. And secondly, precise provides us with many communication, data mapping, and parallel methods. And we use the compact TPS-C2 ratio basic function in our study. And it is improved based on the thin plate function. And in order to improve the computational efficiency, we introduced the tight branch ratio R in the study. And when the distance between the fluid grade and the solid grade is larger than the ratio R, the ratio basic function is 0. Which make the matrix distributed and bending. And in the simulation results, we choose a benchmark simulation, and this is the 2D dimensional size of the fluid field, and the parameters of the structure is in the table. And there are 4 measuring points in the lower part of the elastic beam, and the upper part, the right part, is fixed. And this is the grade of our study. And because the fixed part of the upper grade, so the upper grade is relatively close, and the lower grade is fine. And we studied 3 types of fluid meshes to do the mesh sensitivity work. And it could be found that the fine mesh shows the stability of the fluid field. So we used the fine mesh to do the work. And because it's a 2-dimensional simulation, the fine mesh is just 14,000. And we compared the simulation results with the literature, and the literature used the single-phase delta SPH model. And this is the results of the Matterpoint M1, and you can see that there are slightly different in the second peak of the simulation results, and the error is 2%. And M2's results error is 1.3%. M3's result is 1.5%. M4's result is minus 3.8%. However, we can see from the figure that the first peak of our simulation results is smaller than the literature and experimental results. This may be because the absence of the gate in our simulation will affect the waterfront of the dynamic wave. And secondly, the displacement, the history of the displacement after 1 second shows escalation in our simulation. Let's check the fluid field of our simulation. We can see that after the fluid field, the wave touching the elastic beam, and it will roll and close, and they are entrapped in the air. Because the literature result is single phase, so it may don't observe this phenomenon. And this is 1.28 the fluid field compared with the literature results. We can see because the bubble didn't touch the elastic beam, so the error, shows of our simulation and the literature results it's relatively the same. But however, when it comes to the 1.35, we can see as the bubble get closer to our beam, and our beam shows displacement, shows escalation, and this is 1.50, and we can see the results of the effects of our bubble, and we show escalation, and there are a large a big error between the literature results, and another reason that the experiment didn't observe this phenomenon because in the experiment there are 2 narrow gaps between the elastic beam and the side walls of the experimental tank, and the water may flow through the gaps. So this may also have a significant influence on the fluid field. And then we come to the conclusion. The proposed method is carried out to study the problem, and the numerical results are in good agreement with the experiment and the literature results on the second peak. And the absolute error is less than 3.8%. A smaller result lies in the first peak value compared with the experiment and literature, which may be caused by the absence of the gate. And the entrapped air bubble plays an important role in the overall flow evolution of dam breaking wave. And further works would concentrate on more elastic dam break cases and extend the 2-dimensional simulation to 3-dimensional simulation. And the proposed method could be used in the elastic wedge impact problem. That's all. Thank you.
Okay, thanks for your very interesting talk. And any questions to the presentation? Any questions? Okay, I have a quite question.
Yeah.
Have you ever tried to simulate the 3D problems by your proposed method? If you tried, how's the efficiency of the coupling method?
Yes, I have tried, but this is our further works. But if you try the 3-dimensional, you will extend the 2-dimensional to 3-dimensional, and there will be some mapping problems in the 3-dimension the direction. So it will cost more calculation resources and time. But we are trying the results.
Okay, have ever compared this method with other methods in the efficiency aspects?
Not yet, but we will learn into it.
Okay, thank you very much. Thanks again for your very interesting talk.
Thank you.
Okay.